Hey everybody, I'm Ben, and today I'm going to be talking about building a video processor with Swift and Metal. Really briefly about me, I'm one half of the team that builds two popular iPhone photography apps, Spectre, which is used for generating real-time long exposures. So we use Metal to blend multiple frames together to create this long exposure handheld. And Halide, which is a manual photography app that also, in addition to supporting RAW, we have a depth mode that's similar to portrait mode in the first-party camera. And in that case, we're actually combining multiple video sources in real time to give you this cool preview. I'm going to return to that a few times during the talk as an example of some of the concepts we're going to be talking about. So I'm going to structure this talk in 3 sections, where I'm going to start by talking about the architecture of a real-time video renderer, some of the performance bottlenecks and how to get around them in the second part. And then I'm going to talk about some of the nuances of working with image data, which these are usually handled for you if you're using a high-level framework like Core Image or Core Graphics, and when you get your hands dirty, you have to worry about. So I have a lot I want to cover in a half hour, so I'm just going to get started and dive right into architecture. Now, I'm sure everyone here wants me to just stand up here and just spend a half hour reading line-by-line Apple documentation on AV Foundation. Just a wonderful way to spend your night. But I'm actually just going to talk about it at a high level. Okay? So there is a delegate method inside of AV Foundation you hook into, and you say, give me the frames as they come off of the camera. And this is where things get interesting. So inside your delegate method, you kick off your render loop. So every time a frame arrives, you are going to update your internal state, which depending on what your app does, it could be pretty complicated. And then you're going to kick off commands to the GPU, which will execute asynchronously. And these commands could be to perform additional filter effects or different operations on the image, but ultimately you're going to render them on screen or over to an AV asset writer to write it out to disk. Most of your work on the logic side and updating your state is going to be done in Swift, and then everything GPU side is going to be done in shaders. And if you've ever done game programming, this loop probably seems really familiar because it's almost identical to a game loop where you have a timer firing every 60 frames a second, you process the data, the queued up inputs, and you dispatch the GPU to render. Cool. So I don't think a lot of people here have a lot of experience in GPU, so I'm going to spend a lot of time diving into that. And there are 2 tools available through Metal. The first one, which I'll spend most of my time talking about, is the compute pipeline. And this is a fairly recent idea. By recent, I mean the last 10 years. And the idea is that you can use a GPU as a general purpose programming platform. Which means if you aren't using it for image editing or image effects, it's probably Bitcoin mining. Any problem that is massively parallelizable and probably involves matrices lends itself really well to GPU processing. The second pipeline, and the original reason that GPUs were invented, was for 3D games. So there's a separate path you can take that's optimized for rendering 3D content, but it's a little more complicated. So let's just talk about things from the compute pipeline because it's the simplest to understand. So a shader is a tiny little program that runs in the GPU massively in parallel. We're talking about hundreds of threads executing at once. And in an image processor, you're probably executing 1 thread per pixel of your image. Okay? The language itself, I'm sorry, it's based on C++, a subset of C++11, and Apple calls it Metal. So there are a couple annotations there that make it look a little different than normal C++, but I'll talk about that in a moment. All that we're doing in this Hello World shader is we have this bitmap that comes in, which I'm calling inTexture. I'm reading an RGB value into a half float, and I'm writing it to the output image. So it's just taking an image in and writing it out to an output image. Notice that I'm referring to them as textures. And this is a very GPU-specific term. You could think of a texture as like a super powerful abstraction around a bitmap. So whereas with a bitmap, you're just reading color values one by one from a blob of data, when you upload the bitmap to the GPU and turn it into a texture, you can do all these hardware-accelerated operations. Like if you have a float value between 2 pixels, the GPU can actually filter it and blend it for you so you get nice smooth transitions. Lots of tools like that that I won't go into. So how do you kick off that shader to do your work? Over on the Swift side of things, here is a sample of some of the metal you'll write. I've cut out a bunch of the boilerplate setup. But at the start of your app, you declare the different functions that you want to run that are written over in .metal files. And so here we have that hello world shader function that's over compiled for you in Xcode and everything, and it's accessible in your app bundle. So you ask for that function, and you stash it in a compute pipeline state handle. And you stash this at launch, because it can take a few milliseconds to load. And then at render time, at some later point, you set up your render encoder, and you say, set it to that state of that function, and you bind values to the function using, in this case, set texture, or you could set buffers or bytes or samplers or all sorts of different types of parameters. So you have to imperatively say, I want this value inside this slot in my shader. And then you call dispatch thread groups, and it kicks off to the GPU. So again, that double bracket syntax we saw earlier, that's an annotation to the compiler to let it know what you're expecting to slot into that parameter in your shader. So when you write set texture index 0, it knows to plug it in there. Cool. So that's the simpler option. And the 3D pipeline is a bit more complicated, where there's multiple stages to it. I'm not going to go into it because honestly, it's like the GPU compute pipeline, but just more complicated. But the idea, why would you want to use the 3D pipeline then? If you look at Apple's documentation, they tell you explicitly that the rendering pipeline, the 3D pipeline, is the fastest and most efficient way to display something on screen. They can take various shortcuts when they know that you're not going to be reading values from a texture later. So if you're rendering something on screen, it's highly recommended that the final step is to use the render pipeline to put it out on screen. Fortunately, it's really easy to do that even if you're rendering a 2D image. You're going to basically render the world's most boring 3D scene. You take four vertices, and you cover your screen with a flat plane. You just cover the viewport with a flat plane, and you render a texture map on that flat plane that covers the viewport. Cool. So when would you want to use each? As I said a moment ago, the render pipeline is the most efficient. But one other situation where it would be useful to understand is, let's say that you want to render a UI like the group FaceTime chat window, where you have multiple planes and some of them are occluding other ones, right? Well, if you use the 3D pipeline, it's actually smart enough if you render multiple flat planes to know that this image, the corner here, is covered by this image, and it will discard that geometry, and it won't do what's known as overdraw, where you're rendering stuff that never actually gets displayed to the user, so it's just wasted resources. And this can all be handled on the hardware side. So you just submit the geometry and say render it, and it'll know, okay, I'm going to skip this, I'm going to skip this. So if you're building something that looks a lot like UIKit, you probably want to ultimately use the 3D pipeline. But if you're just doing straight up image filtering, then you probably want to use the compute pipeline. Cool. So I'm giving this talk at Slug, so let's actually talk about the Swift things that are really nice. The first thing, and you mostly know this from working with Objective-C, but the interoperability with C is awesome. So the way that you communicate with shaders and pass large bundles of data back and forth, well, you could have 40 parameters that you pass in, or you would wrap your parameters in a struct and pass that down. The arrangement of the struct matters. You're just sending a buffer of bytes. So you're probably, well, you'd normally want to use C. But what's really, one caveat there, though, is if you're maintaining separate structures in Swiftland and Cland, and you add a field on one and not the other, everything's going to fall apart. But what I do is I create a header file that defines the structures that I use in both Metal and in Swift. And Swift is happy to be like, oh yeah, I can totally instance that, and it'll be identical to what I pass to the GPU, and I can keep the two in sync. So here, I instance it just like any other Swift struct, where I pass it the parameters I'm expecting to pass down, and I can pass it into the index 1 in the shader, and it all just works. Now that syntax is pretty gnarly, and it's imperative. And because of now with Swift 5.1 function builders, I'm starting to play around with building a DSL like Swift UI, where I can actually declaratively define how I want my different parameters to be passed down into the shaders. And it does nothing other than makes it much more clear what is going on as I'm passing data back and forth. Okay. One last thing I want to touch on that segues into performance. As I said earlier, everything that's going on is asynchronous. So we execute commands in the GPU. They're sent off, and they'll probably execute a few milliseconds later, and you don't want to block when you execute these. There is an API to say execute this and wait for it to return. You don't want to use that because you're constantly receiving frames in this loop, and you never want to block it. It's also your responsibility at the end, when you're done producing the frame, to recycle the resources. You could think of it almost like with UI table view recycling, but with much worse consequences, because what is a 12 megapixel image? How much memory does that take up? It isn't 12 megabytes, because 12.5 megapixels has 4 image channels, RGBA, which means every image at 4K takes up 48 megabytes of memory. So it's very easy to run out of resources, and don't even try to allocate that in 16 milliseconds on every frame. So you have to be extremely conservative with resources, which is the main pain point in performance. So, all right, so one example where we run into a problem with the portrait mode that we have is the data that comes into us, this depth data, it's unbounded, it's in meters, and I need to clamp it between 0 and 1 to use it as part of my filtering effect. And so in order to do that, I need to find the minimum and maximum value in an image of 10,000 pixels. And I have to do that in 30 milliseconds. If I were doing 60 frames a second, then it would be 16 milliseconds. So I got to process a lot of data in a very short period of time. Okay? Now, if you were to ask a game developer, how do you make your program fast? They would tell you that the CPU has nothing to do with it. Thanks to Moore's law, CPUs are plenty fast. They're great. They're amazing. And memory has not gotten any faster for the most part. It's mostly been flat for a couple decades, right? So in all likelihood, when you have a performance problem locally, it has to do with memory access. Okay? The way that you can usually hide this is in modern computer architecture, your memory is laid out in hierarchies. So you have main memory, which has like 1.8 gigabytes. But on the other side, right next to your CPU is a L1 cache. It's a tiny bit of memory that's actually located on the CPU die. And it is blazing fast. If you can't fit all of your data in there, as it fills up, it pushes data into an L2 cache, which is larger and slower. And then as that fills up, it pushes data into L3. Some hardware has L4. But it's a hierarchy of fast but small memory the closer you get to the CPU. Now, I'm going to steal a demo from Scott Myers, who is a noteworthy C++ expert. He's written some great books. And he talks about memory access speeds in a few of his talks. So I'll have a link to him later. But you could imagine memory access here as, let's say that's how long it takes to access L1, about a second. Well, L2 is relatively that fast. L3 is about that fast. And if you have to reach out to main memory, you might as well just go grab a coffee, check Twitter, do your taxes, post some image macros, because it's going to take a really long time if you have a cache miss. Now, you're wondering, what are the different levels when I say small amounts of memory? Using, I believe it's an iPhone 7, so that's the majority of hardware out there. Using that as the baseline, you can expect 64 kilobytes, that's with a K, kilobytes of memory is an L1 cache. You can access that in 4 cycles. L2 is 1 megabyte, it takes about 10 cycles. L3 is 4 megabytes, it takes 40 cycles. And main memory takes 30 times slower than L1 cache to access. Now, there's other stuff you can also think about, like when you access memory, it can prefetch lines, which are known as cache lines. There's instruction caches, but I'm simplifying everything to get the idea across that most of performance is based around using as little memory as possible and arranging your data in ways that you work with these caching facilities. So for more information, check out Scott Myers, but also Mike Acton, who's the former engine director over at Insomniac Games. They made that awesome Spider-Man game last year. And they talk a lot about data-oriented design, which is about structuring your app in a way that your hardware can just, well, use basically to run in a straight line and access data as fast as possible. So that usually means arrays or arrays of structs, but just arranging everything continuously in memory based on your access patterns. So let me give you one of the practical implications. Let's say that you're building Stardew Valley, and you have this entity in your game, a wheat patch. It's a grid of wheat, and over time it will grow, so you're going to want to increment its height. And how would you represent this? Well, if you're an object-oriented programmer, of course you start by designing a class called wheat patch that probably inherits from 10 other items in the hierarchy. And then you have a position property, which of course is a class, because you might want to have a subclass of position. You have this height property, but. Now, these are objects talking to each other. We'd never want to reach in there and violate the law of Demeter, and actually modify its value. No. You send it the grow message to make sure it increments its counter. And then you have the maximum flexibility someday. So this is enterprise game development. This will slaughter your performance in most OO languages. For one, classes tend to be just sort of thrown about all over the heap, so you can almost guarantee that you're not going to get free paging in of multiple instances at a time. They're just all over the place, like glitter. They also have dynamic dispatch by default, especially in Objective-C, so you're going to miss the instruction caching, and so it's going to be looking up instructions, which will also cause a stall. And just philosophically, you're looking at a problem in terms of isolated instances instead of in batches of data that you're going to want to process all at once. The reason that Swift is awesome and compelling compared to, or on par with C++, starts with that last section where we talked about explicit data layout. You can make sure that you pack your structs to make use of every single bit in as small amount of space as possible to fit as much as you can in your various cache levels. By default, it uses static dispatch, so you're going to be hitting the instruction cache more often. And just philosophically, it encourages you to look at the problem in terms of values instead of these abstractions that are objects, although it finds a nice compromise where you still have some of the nice message passing through protocols, but without any of the dynamism that costs a lot of performance. Okay, so if the left is the cliched OO approach, here's the most data-oriented design you can come up with, where you'd have an array of arrays, and implicitly, the position in those two arrays declares its position in the grid in the game. And of course, we use a uint to use as little space as possible, and then when you have to increment all of the numbers, your CPU can just run in a straight line and update it, which is great in a game loop. So even if you don't have to operate at that level, it behooves you to think about the data and how you're processing it, because really it's a way of thinking. So let me give you an example that doesn't involve code as much. So for example, in that portrait blur, we have to apply we do something a little different than a Gaussian blur, but let's say you have to apply a Gaussian blur. A Gaussian blur has a time complexity of big O of n times r squared, which basically means when you want to create a really blurry image, it's going to slaughter performance. It explodes in the amount of positions it has to sample in an image to produce this nice, beautiful blur. So there are alternative approaches to blurs that approximate a Gaussian. Some of them give you these weird artifacts, which if you're just having a background blur like in UIKit, you can get away with. But if you want something really beautiful, nothing really beats a Gaussian. So what if we shrink the image to 1/4 of its size, then apply a Gaussian, and then upscale the blurred version? I challenge anyone in this room to tell me the difference between these two images. The one on the left, I downscaled, applied the blur, and then upscaled, and the right is the true Gaussian. It means that we're processing 1/4 the number of pixels, and the radius of the blur is about half of at the full size. So it wins on both sides. Cool. Awesome. And that transitions us into the third section, where I can apologize for some of the nuances you're going to run into when you're processing this data. Knowing that memory is a constraint, just keep that in the back of your head. Because you get to this point, you have your shader set up, you have the images coming in, and you have this image that came in from the camera, and you expect it to output like this. But then when you go and render it, you end up with this red image. It's missing a couple of color channels. That's weird. What is going on there? And it turns out the system is giving you actually 2 images for every frame of video. That's weird. And one of these images is actually this grayscale 1-channel image, and this is a 2-channel image. And this is known as YUV color encoding. And what happens here is it splits up the image into its brightness values and color values. The UV refers to its position in this plane of different color values. It's also sometimes called YCBCR. The CB stands for color blue, CR stands for color red. So if you see those used interchangeably, they all mean the same thing. Why are they splitting it up like this? Okay, I had to shrink this because I'm putting it up on a projector, but this is an optical illusion you might have seen on the internet. It might be too high fidelity even to the size, but remember this thing that went on Twitter a couple months ago, where it looks like all the kids in this photo have their shirts in different colors. But if you then zoom in, it turns out all the shirts are grayscale, but then this crisscross pattern is the color. And that's because, I'm going to do a couple more visual optical illusions, this is great. But the reason that this happens is because our eyes are more sensitive to shifts in brightness than to color. So this has an interesting implication. So we have this image that's separated. We can actually store the 2-color image 1/4 of its size. And because it's 2 channels and luminosity is 1 channel, the total savings is about 50%. 50% less that has to be passed around, conserving bandwidth. The down part is you have to convert it back to RGB to display it on screen. And for whatever reason, Apple doesn't include the sample code to do this in Metal, but recently they included it in ARKit. So I have a link at the bottom, but all you have to do is copy and paste this code, and it's one matrix operation to get back to RGB. It isn't that difficult. It's not that intimidating. It's okay in this case to just copy and paste these magic values. Or you could go watch a college class on online to understand it, but it's not hard. What is hard is the system gives you these metal textures which mean nothing. They're just blobs of data. They could mean luminosity, they could mean RGB, they could mean color, they could mean anything. So it's up to you to keep track of it as you're passing it into your different subsections of your render loop. And so the way I do it is I just use structs to wrap the values, one to make sure that the 2 textures are always coming along together as best buddies, and making sure that I know explicitly this texture represents RGB, and that way if I forget to implement in a shader support for one format or the other, then it'll catch it at compile time. Cool. So, all right, so we've got it displaying on screen, but then it turns out it's way too dark, or it could be displaying way too light. What's going on there? You don't need to check your monitor. So what's going on, let's imagine for a moment, in our heads, a perfectly linear gradient, something like this. You probably think on a scale from 0 to 100, or in this case 255, that the 50% value sits right here. In fact, if you were to write a loop that just outputs values on screen linearly like that, it would actually look more like the gradient on top. And the reason is that our eyes are more sensitive to shifts in shadows than highlights. So that means that, in fact, you think that 128's in the middle. In a perfectly linear gradient, it's way over here on the right. And this has a very bad consequence because you only have those 128 values now to represent all of this. So I've never once been able to give this demo on a projector that's been able to properly show it. So I have a link at the bottom so you can see on your monitor. But I also, in Photoshop, blew out the gradient to really show it. But what happens is that when you have so few bits to work with, you end up getting banding at the low end of the gradient. So you're going to lose details in the shadows, and your photos are going to look off. So this is the source of the bane of your existence. gamma correction. The idea is you take a photo with a camera, let's say. Those values in the real world are all linear. Before you encode it into bytes or save it to disk or whatever, they are lifted up using a gamma curve to make everything seem brighter, just so that there's more bits to work with. And then when you go to display it later, the inverse of that curve is applied so that it's output to the monitor and it looks correct. Okay? The reason this is the bane of your existence, and I strongly recommend understanding gamma correction, is that if you have to do a calculation, like saying, I want to blend two images together at 50%, if you're doing it in this gamma space, then your calculations are going to be totally off. And again, Apple provides sample code, this time in a PDF file, so it's a little harder to copy and paste. And it's literally the second to last page in the metal shading language specification for getting it into linear space. I don't have a type-safe solution to that. It's just a matter of making sure you pick one space to work in, and everyone's working in the same space. Kind of like if you ever ask a server person, what should I set my the clocks on our server to? They'll be UTC, UTC. So think of gamma and linear as like the UTC of spaces to work in. Just everyone agree on one and stick there. So here's the last thing that will annoy you. And this is a more recent problem the last few years. You go to render it on screen, and if you have really sharp eyes, you'll notice that the red is slightly off from what you're expecting. Or you won't notice it, and you'll ship it to production. The reason for that starts with this horseshoe, which represents the entire visual spectrum. Our eyes can see everything there. And for several decades, we could only represent the stuff in this inner triangle in that spectrum on computer monitors. That's known as the sRGB color space. And that was fine, but then Apple ruined everything by releasing displays that can display more content. And now you have to keep track of the images that are coming in through the system and what color space they're originally in and how you're going to output it on screen. So we just add to this lightweight wrapper, you just add a tag there for color space and then add various affordances and also exhaustive enumerations to make sure that you support both color spaces inside of all of your methods, and you should be all set. And again, you just pick one color space for everyone to work in, and everything should be fine. Cool. And you end up with the final image. So what did we cover today? 1, the render loop. 2, talked about shaders. 3, and I think the most relevant thing for everyone in this room, is a data-oriented approach to system design. And the reason that Swift is so powerful is the ability that you really don't get any of the compromises that you'd get in other systems. You can get great performance, you can get a language that's perfectly suitable for game programming, but you get all of the niceties of something that isn't based on C++. And finally, I talked a little bit about keeping everything in order on YUV, gamma, and color spaces. So yeah, that's everything I want to talk about. And we're going to take questions at the end, right? Now? Okay.
Give it up for Ben. All right, we'll take 3 questions. Please raise your hand, and I'll come to you with the mic.
Did you have any experience with shaders working with other game engines or other languages before it, or was learning Metal and like their version the first take you had at it? I'm just kind of curious, was it a good take, or like how confusing was it to actually pick that up?
Good question. So the alternative right now is, so the question, well, it was already on the speaker, so I don't need to repeat it. So the alternative to Metal is OpenGL, and now there's a newer version from the same working group that created OpenGL, Vulkan. So I'll say OpenGL was created in, say, the 1990s before GPUs were even a thing. They're a terrible abstraction now, and that's the reason Apple invented Metal. So I learned Metal and OpenGL in parallel, but I'm really glad Metal existed because it kind of did away with all the abstractions that OpenGL no longer fits around it. So it's a great way to start now. So with Vulkan, I haven't played too much with it, but I've heard mixed things. So if you were to start it right now, I'd say just dive into some tutorials on Metal, and then it's much easier then to go back and learn all the sharp edges around OpenGL. Cool.
I have a question. have you come across any good tooling to determine how much of your memory is actually being cached in the different cache lines of the CPU?
So I believe dtrace can do it, although that doesn't really solve. I don't think you can run dtrace on iOS, right? So I think, and Scott Myers says that you develop an intuition around these certain things. So when you notice that you're having issues like false sharing, it's like, oh, okay, am I accessing the same value for multiple threads? But I believe there are like counter tools in Mac dtrace, but I haven't run across one on iOS. So really though, I think with a lot of this, you're not going to be able to, on the 11th hour, run into, oh, I'm having performance problems, and oh, I just have to fix this one bug. It's really like, wait, you didn't structure everything in advance. You're already doomed. So you just kind of have to be thinking about it from the design side, I think.
One last question.
Would you prefer to build this in C++ over Swift, or what are the benefits of maybe doing one or the other, in your opinion?
Good question. So C++, well, Swift doesn't exist anywhere outside of Apple platforms. Let's be honest with ourselves. Like, if you're really brave, you can run it on the server side, but I wouldn't touch it on Android. Like, it's just not there. So if I were doing something cross-platform, no question, I'd just be using C++, and my heart would go on like, man, I really wish I could use Swift. As far as like, again, well, I think especially with game programming, there's just also a larger community. So when you run into a problem, you're going to have way more people that can answer it and sample code if you want to do a shader. So I've had to, and going back to OpenGL, I have, for certain effects, there's like Shader Toy, which uses WebGL, and I've looked at that and in my head translated, okay, what is this in metal shading language? So you lose a lot of the community when you go down this path. But yeah, I can be super selfish and just write everything in Swift. But if I were on a team or doing cross-platform, I'd absolutely use C++. Cool. All set.
Thank you.
Thanks.
Thank you, Ben.